Okay, so the question that usually people start with is, what's the difference? If we have a data center where the machines synchronized against a common source, what is going to happen? Where do you going to see any improvements, or how can we increase the efficiency just by synchronizing the clock? And this is not a new question. It's a question that we've been asking for many years. In fact, in the late 80s, beginning of 90s, people looked at the NTP protocol as the answer of synchronizing machines across long distances. And there was a few papers that shows you can use the clock to replace communication with local calculation. There are certain type of algorithms and protocols that can benefit from synchronized clocks. And the benefit comes with higher efficiency. You can use the clocks to run faster most of the time in these protocols. And there are a few occasions where you can use the clocks to run with, to protect the correctness of the algorithm and the protocol. The difference between 10, 20 years ago, actually 30 years ago, and today is that today we have PTP, and PTP is much more precise than NTP. When in NTP we talk about tens and hundreds of milliseconds, in PTP we talk about tens and hundreds of nanoseconds. When we get to this level of precision, we can go and execute these protocols in the data center where the network latency is fairly low, not just across data centers where the speed of light is the limitation that set the latency in the range of milliseconds, sometimes hundreds of milliseconds. Today, I'd like to share with you a few of the cases where we can successfully replace communication with local calculation and take the benefits of synchronized clock in the data center. Some of these cases are famous in the industry, like external consistency, that was an external consistency and the commit wait protocol that Google announced about 10 years ago as the core of the spanner system. Others, like authentication tickets and Kerberos, has been in the industry for quite amount of time. But today with PTP, we can go and make them much more efficient. At most one message is a problem that has been discussed for many years, and it's a difficult problem. By utilizing precise times across the whole network, we can minimize the window where we need to keep the messages and compare whether the message was handled before or not. Making cache consistent with high precision is another place where the clock can help us to invalidate the cache on both sides at the same time, or making sure that the data has not been modified when we serve the data from the cache. Commit window is another place where today, when we have a Paxos ring or Raft ring, we have this tendency of competing with the timeouts. And when we have precise clocks, we can shrink these timeouts and increase the availability of the system. We can go from hundreds of milliseconds to hundreds of microseconds. And the effect to the behavior of the system is that there are very few cases, the system is capable to restore back the viability, the work, and decrease the viability much faster than before. Let's talk a little bit more about the external consistency, because the external consistency is one of those things that can change completely the behavior of the system in respect of the client. External consistency allows building geo-distributed systems that are indistinguishable from a single machine database. And the clocks are not the technology that enables this. The clocks are technology that makes this to work in a very efficient manner. In external consistency, we have the guarantee that any completed transaction change the system in a way, change the state in a way that any transaction that starts after that is going to see the result of all previously finished transactions. The result is the client applications can rely on consistency level that removes all the complexity from client application and keep the complexity in the data center, keep the complexity in the underlying services. That allows building not just more efficient system, that allows building the system that naturally easier to reason about, and systems that have fewer problems when we talk about behavior of the system. But let's start first with what happens if we have a system that is not externally consistent. That is easier to describe. And here we have an example that might be a real example. A few years ago, we had a very interesting game, the finals of the soccer World Cup, Germany versus Argentina. And we have 3 agents or 3 entities. In fact, 3 people. Alice and Bob are in a restaurant somewhere. They are very interested from the final, from the game. They want to know the final result. The referee is the person that's going to announce the end of the game. And let's imagine that, in fact, that happened. Germany scored. The result of this is the referee announced the score as 0-1. That was sent to a system where we have a leader and 2 followers. And just for the discussion, let's think about this system as a system that is highly available and replicates the data across 2 followers. So any update needs to be acknowledged by quorum. When the leader and one of the followers acknowledge the change, we consider this change as a persistent change that should stay in the persistent storage and should be considered as change in the state. So when the leader sends the result arrives at the follower 1. It just happened that we have this network latency that is at this point much higher, and the follower 2 is going to get the update a little bit later. So now Alice wants to check what is the score. Alice goes to the follower 1 just because her device decided to go to follower 1. And the result at this point of time in follower 1 is 1-0 and the game has ended. So from Alice's perspective, the Germany has won the World Cup. At the same time, Bob, using his phone or mobile device, look at the follower 2. Naturally, that can happen for a variety of reasons. It could be load balancing, it could be different provider, but the follower 2 doesn't know about the end of the game because the update from the leader has not arrived yet. And that's perfectly fine, and it can happen for many reasons. So the follower 2 doesn't know the result, and Bob gets back an information that is a stale. From follower 2 perspective, the game hasn't ended. So now we have this inconsistency, and inconsistency is really bad for the client experience. From the user point of view, a system that you can rely on supposed to have these beautiful properties that anytime when you ask the system, it gives you the same result. And if 2 people ask us the same question, they're supposed to get the same result. And this looks like an artificial example. You can think about much more interesting and more important example, like let's imagine that the referee acknowledged that Alice doesn't want to see anything from Bob, just blocked Bob. But the server where Bob landed still hasn't gotten the update. So the server is going to allow Bob to continue communicating with Alice, even though from Alice's perspective, the communication between her and Bob has been blocked, and the system promised that no other messages will arrive. So inconsistency is not a good sign. And when you talk about some other cases like bank or insurance industries, inconsistency is considered as unacceptable. So how can we fix that? The simplest thing is, let's ask Bob to go to the leader, and let's ask anyone that wants to know what the state is, go to the leader. And that works. In fact, there are multiple systems that rely on the fact that if everyone goes to the same machine, the order of the events is preserved and the state is managed in a very predictable way. But usually going to the leader when you're talking about a distributed case is expensive. And it could be quite expensive. In this case, I put 42 milliseconds because we have internal example of data centers that in about this range between each other. So the total request is going to be about 80 milliseconds. At the same time, it doesn't matter whether Bob goes to the leader or Bob goes to the forward 2 and the forward 2 goes to the leader. In both cases, from Bob's perspective, this is 80 milliseconds latency. And that is pretty bad because the latency between Bob and the forward 2 is just 1 millisecond. So if Bob was able to get the data from the forward 2, the total request will be just 2 milliseconds. And that's a 40 times better than this 80 milliseconds. So now, how can we change this? How can we improve the situation just by introducing precise time, and every participant in the cluster has a clock that is accurately and precise. That requires not just introducing the clocks though, that requires a little bit more, but it's very small change. So now every request that is going to mutate the state or is going to observe the state, read the state, should come with a timestamp from this clock that, from a synchronized clock. So the request that update the database from the leader carries the timestamp that is a result of reading the local clock of the leader. So there is no going outside the leader. When Alice or Bob wants to read the data, their request lands to the respective forward. And the forward 1 is going to check whether the data that Alice needs has already been updated, or we have a message from the leader that carries a timestamp bigger than what Alice asked for. That for Alice, that doesn't matter so much, even though the diagram is a little bit off, but it's more important for Bob. So when Bob's request lands, the Bob requests come with a timestamp that might be in the past, and then we can directly read from the forward. And the total time for the request is going to be just 2 milliseconds. But if it happened that the Bob request is in the future, then we can wait or request from the leader. Most of the time, this can happen only if the forward 2 was not part of the quorum. But if the forward 2 was part of the quorum, that is the general case, the case that we observe most often, then the forward 2 has the data, and the forward 2 returns the data immediately, and the total request is about 2 milliseconds. So just by introducing precise time, we can go and shrink the latency in respect to the network latency in tens and hundreds fold, depends how far the entities are. How can we implement this? In practice, the first example that I'm aware of is the commit wait protocol. The commit wait protocol was published by Google about 2008 as a part of their Spanner paper. And I think it's a very clever way to use the time, because it doesn't require to have infinite precision. The protocol is based on the fact that you can measure and manage the clock uncertainty with very high level of confidence. And now when you ask what the time is, you're not getting back one timestamp. You're getting back a range that guarantees that the time is somewhere between. You don't know exactly where, but we know that there is in this interval, earliest, latest, somewhere between them is the real time, the universal time. So when you want to commit, when you want to write, you have to choose a timestamp. And the timestamp is chosen as the latest of the interval that you're getting back from the clock. That means even though the real time might be somewhere behind, we guarantee that the real time is not higher than the timestamp that we choose for the transaction. After that, we have this additional delay, and this is an important point. This additional delay requires the system to pretend that the data has not been updated until we get another range where the timestamp is definitely bigger than the timestamp that we chose. So we wait until that happens. And when that happens, we return back to the client, acknowledge that the transaction has been successfully committed. Now, when we want to read, what do we do? Again, we use the range, but this time we choose timestamp that is the latest. And we go and ask the data for this timestamp. That guarantees that any transactions committed before we started is going to see the outcome of the committed transactions. And that works really well. So I'd like to point that here, the wait part is very important, and it's important for the correctness of the protocol. The difference is if you use NTP, the wait part is in the range of hundreds of milliseconds and makes the protocol less efficient than exchanging or communicating between the nodes. When we go with NTP, the wait part can be in the range of nanoseconds, hundreds of nanoseconds, or a few microseconds. In the nature of the execution of the transaction, we're going to consume this time just by executing the code. So in commit wait with PTP, we are having this beautiful commit zero wait. So you're going to execute the transaction, but because the transaction requires time to be finished, time to be executed, at the end, you just wait zero. And that keeps the efficiency of the system high, the transaction throughput, the latency low, just by introducing precise time. And you also guarantee external consistency. So that's beautiful. What are the challenges? What makes it difficult today to go and execute this at scale? So we have two worlds, the hardware and the software. And they want to cooperate to build a system that allows transferring the data back and forth. But today they have very different, different limits on how well you can manage the time. So on the hardware side, we have tree type of structure where on the top of the tree, we have this grandmaster. And the grandmaster is usually a clock that's synchronized against GPS or GNSS. And the natural error or the error bound that we expect for the grandmaster is in the range of hundreds of nanoseconds. The grandmaster disseminates the time, the precise time using PTP through a sequence of transparent and boundary clocks. The transparent clocks, they count the time or they measure the time of residency and they subtract that. So at the end of the calculation, the time that was spent in the transparent clocks or the device that behaves as a transparent clocks is subtracted from the total time. And the boundary clock behave as on one side as an ordinary clock and on another side as a grandmaster. The ordinary clock, the boundary clocks, and the grandmaster, all of them have error bound in the range of 10 to hundreds of nanoseconds. And that's an excellent result. That gives us high confidence, keep building a large network where the time is synchronized in the range of hundreds of nanoseconds. The challenges, in my opinion, are bigger on the software side. Because in the ordinary clock, we have this NIC where the clock on the NIC, the PHC, is synchronized to hundreds of nanoseconds. But bringing this to a service that's running in the user mode is a task that today requires a little bit more effort. before we get to the CPU, we need to get through the PCI bus. And today, you can use some technologies that PCI bus provides to measure the time, but that is a relatively new technology, or it's not available in all data centers. So you might expect tens of microseconds delay. And this delay is not constant delay, so it's kind of hard to be predicted. After that, we land in the kernel world. And the kernel, or kernels that we run in the data centers, they are not real-time kernels. And you can run real-time kernel. I don't know how that will look like, but the kernel that we use by default is not real-time. So you might expect some level of delay, some delay on the kernel side. And in the good cases, in the best cases, we are measuring in the range of microseconds, tens of microseconds. This results a result of tests that we did internally in data center hardware. And getting outside the kernel to the application requires going through some level of libraries and APIs. And most of the time, we are getting really good results. But from time to time, based on how busy the machine is, we measured differences in the range of milliseconds. So we come, based on the advancement in PTP stack, we come with a solution that I'm going to talk about in, I think, an hour later in one of the next presentations. But today on the software side, we don't have a very good way to be as precise as on the hardware side. So we have this environment where we can spread around precise time in technically millions of machines to the clock on the NIC. And now, after that, getting to the application, we're losing most of this precision. So instead of being in nanoseconds or even microseconds, we're landing in the range of milliseconds in the worst case, not always. But in the worst case, we can easily be in the milliseconds. There are a few options, and as I said, I'm going to talk about this in the next presentation. I think today the technology is advanced enough, all of us, to start thinking how we can use precise time to make the system faster, more efficient, and I would say even more reliable. In the software industry, for decades, we were starting with the presumption you cannot rely on the clock. The clock is unreliable. I think today we can make the clock as reliable as the network. So as long as you have network, your time is going to be synchronized. And that requires reconsidering some of the requirements and reconsidering some of the designs. We can use the help that synchronized time gives us and make the system more efficient. But for that, we need to develop a little bit more the end-to-end scenario where you have time disseminated from GPS, going to individual machines and bringing precise time to the application level. So we can build systems that by design use clock to be more efficient. Any questions?
There are no questions yet on the chat. Okay. Let you know if they come later.
We have 5 minutes.
Beautiful. Thank you, Georgi.
Thank you.
One question, Georgi. So when it comes to the accuracy of, like, as you mentioned, like this presented by Spanner, the commit and wait. So do you think the accuracy required for these systems, which we are basically bounding it to being better than the network latency, do you think going beyond this in the future, would there be applications that they can take advantage of it or not?
Can you tell me what is beyond this?
Let's say if we end up like with a distributed clock that is, let's say, in range of tens of, like, let's say, nanoseconds, and going down, let's say, like perhaps picoseconds, or I'm like slowly going further, yeah.
I think it's a competition between ability to communicate between the nodes and the precision of the clocks. If you have a data center where the communication between machines gets to the level of nanoseconds, and I'm not saying that's impossible, you can go to some new technology where the machines communicate in the range of nanoseconds, then you have to have clocks that are better than the communication. If you have communication in 100 nanoseconds, you want to have clocks that is synchronized in the range of tens of nanoseconds. That's when you want to run in the same data center. If you want to run between data centers, then the speed of light is the real limit. And I think we can compete with speed of light very successfully by using spreading the time ahead of the communication. So you have these magical balls on both sides of the communication that tick with the same speed. And then the speed of light is going to be the limit between the machines. Mm-hmm. If you're in the same data center, I predict the communication speed will continue increasing. So today we can communicate in the range of tenths of microseconds, but I've seen experiments where it goes below 10 microseconds, communication between the machines. So I think if you want to be on the safe side, we should target network synchronizing clocks in the range of nanoseconds in the next decade.
So
we have a question.
Sure.
From the audience. Hey, hi, Alon Regev from Keysight is asking, any work being done on reducing the time uncertainty added by PCIe using PTM or similar? The time is nodding.
So there are two parts. Oh, great. So PTM is definitely the answer. The challenge is that if you don't have PTM in your data center, maybe using proprietary solutions from hardware vendors is the fastest path. But in the future, not just because of time, it just natural improvements in the PCI would make PTM to be just by default enabled on the PCI. If that's not the case, we have other ways to try to manage that, but it's absolutely necessary for getting to the point of predictable environment where the software stack can get access to this well-synchronized PCH clock on the NIC.
I would like to add, with your permission.
Sure, go ahead.
Please.
Go ahead.
So first of all, yes, it concerns us a lot because we bring a huge accurate solution and we cannot deliver it to the end goal. So it's like the last mile, almost the last mile. So it does concern us. And I second Georgie, PTM is the long vision. This is something we need. And the call for action that I would like to recommend that anyone that hears us is that when you buy a server that supposed to used for real-time or synchronization, ask the vendor about PTM support. I think that the requirement from the field will create a change. And second, we are going to rely on proprietary solution in the near future. So we will have a solution, and long vision is indeed PTM.
Thank you, Dotan. I don't see further questions, and we're very close to the top of the hour. Anyone from the audience?
Okay, join us in the next presentation where we will talk about some of the software solutions that we're proposing, and maybe there are other options too. Thank you.